Hello, guys and gals. In this video, I'm going to be going over some of the practice problems that we had. We're supposed to go over them in class, but if you missed, this will be a good chance for you to catch up and see what's going on, okay? So, in practice problem 1, we have the reaction between a chlorine ion and a hypochlorite ion and a hydrogen ion, and they're reacting to make chlorine gas and water, okay? So the question is, what effect will increasing the concentration of the hydrogen ion at a constant temperature have on the reaction represented above? The option A says that the activation of the reaction will increase. The activation energy of the reaction will increase. Well, this is not true. There's not really anything that we can do to affect activation energy, okay? Activation energy is not affected by concentration. It's not affected by temperature. It just is, okay? So A is not correct. The activation of the energy of the reaction will not increase because you increase the concentration of a reactant. B says the activation energy of the reaction will decrease. Again, we're not going to affect the activation energy because we've changed the concentration of a reactant. C says the frequency of collisions between the hydrogen ions and the hypochlorite ions will increase. Well, that's true. Increasing your concentration is going to increase your number of particles. Increasing your number of particles is going to increase your number of collisions, and more collisions means a faster reaction rate. So C is true, but let's double check D just to be sure. D says the value of the rate constant will increase. Well, we don't really know what a rate constant is at this point, but whatever it is, it's not affected by the concentration. Okay, we'll learn about that later. The rate constant is not affected by concentrations. It's only affected by temperature. Okay, so the answer for question number 1 is going to be C. Increasing your concentration is going to increase your number of hydrogen ions. Increasing your number of ions, aka your particles, is going to make more collisions occur. Okay? All right. Question 2 says factors that affect the rate of a chemical reaction include which of the following? And it gives you 3 options. Frequency of collisions of reactant particles, kinetic energy of collisions of reactant particles, or orientation of reactant particles during collisions. Well, the fact is, all 3 of those affect the reaction rate. Those are the 3 requirements based on collision theory. So E is the correct answer here. The frequency of collisions that occur, the energy of those collisions, and the orientation of those particles. All of them affect your reaction rate. All right, let's go on to number 3. If I can get my computer to cooperate. Maybe. Come on. Okay, seriously. I do know that practice problem 3 is pretty complex. So what we're going to want to do is we're going to want to make sure that we're reading all of the information that they give us and that we really understand the graphs and the tables that they've given us. Okay, here we go. So for the equation here, where nitrogen monoxide is reacting with oxygen gas to produce nitrogen dioxide, the initial concentrations of nitrogen monoxide and oxygen gas are given in the table above. The changes in the concentration of nitrogen monoxide as a function of time are shown in the following graph. So what they've given us here on the right is a concentration versus time graph. This is literally showing us what the rate of the reaction is doing as the time goes on. Okay? Under the same conditions, one of the following graphs represents the changes in the concentration of oxygen over the same period of time. Which graph best represents the changes in oxygen and why? So what they're saying is, here's the correct graph for what's happening to one reactant. You tell me which of these is the correct graph for what's happening to the other reactant at the same time. This is a relative reaction rates problem because they're giving you one and they're saying compare it to the other reactant. This is a relative reaction rate problem. Now in the future, you're going to think that this is a rate law problem because they've given you so much data here. But the fact is they're asking you to compare two rates to each other. That makes it a relative reaction rate problem. Okay, so we've got these two graphs, and we can see here that they both start at the correct initial concentration, so that's not really going to help us pick out which one is the correct one. But graph 1 has the same exponential decline that the concentration of nitrogen monoxide has, while graph 2 is kind of more like a steady, almost a straight line. Well, let's think about what we know about the concentration of our reactants during a reaction. Our concentration is going to keep decreasing, and as the concentration decreases, our rate decreases as well. So this line is literally showing us what the rate is doing, and we know that the rate does not decrease perfectly, okay? It's an exponential curve. And so because we know that rate is not constant as we go through a reaction, that's going to be a big hint to us that graph 1 is going to be the correct answer, okay? But let's go through and double check all our answer choices just in case, that way we make sure we pick the right one. So A says that graph 1 is the correct answer because the rate of oxygen consumption is half the rate at which nitrogen monoxide is consumed. 2 molecules of NO react for each molecule of oxygen that reacts. Okay, everything they've said there is true. Let's make sure our graph backs that up. So our initial concentration of the nitrogen monoxide was about 0.0028. If we see what happens initially, it decreases to about 0.19, it looks like. So it decreases by almost concentration of 10, right? But if we take a look at graph 1, we start at 0.0014, and then we go down to about 0.9. So the concentration of nitrogen monoxide decreased twice as quickly as the concentration of the oxygen in graph 1. Does that fit with our relative rate shown by this balanced equation? And the answer is yes. For every 1 mole of oxygen that's used up, you're going to use up 2 moles of nitrogen monoxide. So the concentration of nitrogen monoxide is going to decrease much faster than the concentration of oxygen will. So A makes sense. Let's double check the other ones just to make sure, okay? So B says graph 1 because the oxygen molecules are consumed at a slower rate at the beginning of the reaction when there are not as many molecules of NO2 produced. Well, it doesn't matter how many molecules of NO2 are produced because they're not reacting. So they have no control over the rate of the reaction. They don't matter at all. Also, molecules are always consumed faster at the beginning because you have so many of them. The problem is that after they react, they're gone, and so now your number of molecules has decreased, and so now your rate is going to start decreasing. Your rate is always going to be the fastest right when the reaction occurs because you have your full number of molecules at that point. Okay, so B does not make any sense for 2 reasons. First of all, because your molecules are always consumed faster at the beginning of the reaction, and second of all, because the number of molecules of NO2 produced do not affect the rate of the reaction. Only the reactants affect the rate of the reaction. C says graph 2 because there's a large excess of O2 molecules and its concentration will not change drastically over time. Well, the concentration of oxygen is lower than the original. If we do the math here, I don't think we're going to end up with a large excess of oxygen. But even if we did, the concentration is going to change drastically over time because that's what the concentration does in a chemical reaction. It starts out high and it drastically changes as we go through. It's going to get smaller. That's what concentration does during a reaction for the reactants. Finally, D says graph 2 because collisions between 3 molecules to form a product has a low probability and the concentration of O2 will remain relatively constant. Well, while they're correct about 3 molecules having a low probability, their last part about the concentration of O2 remaining constant still doesn't make any sense. So our best option here is going to be A. Let me know if you guys have any questions.